Hi, and welcome to Chemistry with Jolie, Lauren, and Ito. Today we will be teaching you about stoichiometry. The breakdown of the word itself is stoichion, meaning element, and metron, meaning to measure. But to start, what even is stoichiometry?
Well, Jolie, stoichiometry is defined as the relationship between the relative quantities of substances taking part in a reaction or forming a compound. Typically a ratio of whole integers, but what does that mean? Well, let's put it in terms of baking cookies.
Turns out cookies and chemistry have a lot in common. Just as you need a specific measurement of ingredients to make cookies, you need to have a balanced equation to start a stoichiometry problem. A recipe of a cookie is the same thing of a recipe as a reaction. A list of ingredients or reactants and the final amount of cookies or products is all you need to know!
Take this problem, for example. Here's the equation. 4 eggs makes 2 cookies. Now we want to find out how many eggs are needed to make 4 cookies. First, let's put what is given in the upper right corner of our equation, 4 eggs. Below that, put how many cookies can be made with that number of eggs. In this case, it is given and it is 2. Now we want to cross out the cookie unit, so diagonal from the cookies, put how many cookies we are trying to make. In this problem, it tells us we are looking for 4. Now you just multiply the top 2 and divide by the bottom to get the answer of 8 eggs. Although this problem is seemingly easy and these cookies would be pretty eggy, the concept follows through with more complex problems. Ito, how are the cookies looking?
Pretty well measured.
In chemistry, we use stoichiometry as previously stated to calculate mass, moles, and other units of measurement. Let's apply what we have learned to a simple mole-to-mole problem. The equation is as follows. Blank Al2O3 yields blank Al plus blank O2. First, balancing. So on the left side of the equation, we have 3 oxygens, and on the right, we have 2. Let's multiply the left compound by 2 and the right oxygen by 3 to get a total of 6 oxygens. Now, on the left, we have 4 aluminums, so we have to place a 4 in front of the Al on the right to completely balance the equation. Now that it is balanced, we can figure out the problem which asks, how many moles of aluminum can be produced from 13 moles of Al2O3? Let's start by putting what we are given in the top left corner, 13 moles of Al2O3. Just like with the cookies, we want to cross out alike units, so diagonally, put the number of Al2O3 moles that there are in the balanced mole equation. In this case, it is 2. Above that, since we are trying to find out how many moles of Al can be formed, and we want that as our final unit, we will put the number of aluminum moles in the balanced mole equation, which is 4. Now you just cross out the units, multiply the top, and divide by the bottom, and voila, 26 moles of aluminum. Easy peasy.
Not so fast, Lauren. The problems get way more complicated than that. There are also multi-mass equations that require an extra step. Take the same balanced equation from the previous example. We saw how we got 2Al2O3 yields 4Al plus 3O2. But now the problem asks, how many grams of oxygen can be produced from 13 moles of Al2O3? No biggie. We start the same way by placing 13 moles of Al2O3, what is given, in the top left corner. Next, when attempting to cross out the Al2O3s, we place 2 Al2O3 diagonal from 13 moles, simply because that is what is in the balanced mole ratio equation. Because we are trying to find the final unit to be moles of oxygen, we place 3 moles of O2, the balanced equation numbers of moles, above that. Now, we add the extra step of finding the molar mass of the element or compound. Wait! What is molar mass?
Good question, Ito. Molar mass is defined as the mass of a given substance divided by the amount of substance. We are going to need this here to make a ratio of grams per 1 mole to a given number of moles. So in this case, we need the molar mass of oxygen, which we can find by looking at the atomic mass on the periodic table. It says that oxygen has a mass of 15.999, but you can't forget that oxygen is a diatomic, so you have to multiply it by 2, which is approximately 32 grams.
Thanks, Jolie. Now we're trying to finish with a unit of grams. So in order to cross out the moles of oxygen unit, we can place a 1 mole of oxygen diagonally from the 3 moles of oxygen and put the newly found number of 32 grams, which represents how many grams there are in that 1 mole of oxygen. Now, we cross units once again, multiply everything on the top, and divide by the bottom to end with 624 grams of oxygen.
But it gets a little more complex. The hardest type of stoichiometry problem you can get is a mass-to-mass problem. Take the same balanced equation from the previous two examples. We saw 2 times how we got 2Al2O3 yields 4Al plus 3O2. But now the problem asks, how many grams of aluminum can be produced from 25 grams of Al2O3? Just like we always start with what we are given, 25 grams of Al2O3 in this case, in the upper left corner. Diagonally, in the interest of crossing out like units, we will put the molar mass of Al2O3.
One last time calculating molar mass. If you look up the molar mass of aluminum on the periodic table, it reads 26.98. But we have 2 of them according to the compound, so we will multiply that by 2. Next, we will add that number to 3 times the molar mass of oxygen, which is previously stated as 15.999, to get a total molar mass of 101.964 grams of Al2O3. Back to you, Jolie.
Thanks, Lauren. So as previously stated, we will put 101.964 grams of Al2O3 diagonal from 25 grams of Al2O3, which was given. Now, above the molar mass of Al2O3, we will put 1 mole of Al2O3 because that has how many moles can be made from that molar mass. Diagonally from that, we will put 2 moles of Al2O3 in order to cancel the unit because that is what is in the balanced mole ratio equation. Since we are looking for grams of aluminum, above that we will put the mole ratio of aluminum, which is 4 moles. And finally, diagonal from that, we will put 1 mole of aluminum and the corresponding molar mass above it, which was classified before as 26.98. Now, as always, cross-cancel units, multiply the top, divide by the bottom, and your final number is 13.23 grams of aluminum.
Wow, Jolie, that's a lot of information you've learned from just one simple balanced equation.
Yeah, and aside from cookies and chemistry, stoichiometry can be used in any real-life measurement conversion applications. It's super simple and easy once you know the steps.
But wait, there's more. Add some sprinkles into it.
There's something else we talk about in stoichiometry called limiting and excess regions. Take these sprinkles and cookies for example. Let's say I have 3 cookies and 2 things of sprinkles. The sprinkles in this case would be the limiting region. If you needed a whole thing of sprinkles for 1 cookie, being that there is 1 cookie left over and no sprinkles to cover it, that cookie would be called the excess region. The limiting region, the sprinkles, are what runs out first and what is completely consumed in the reaction. This concept is used in chemistry when you would like to find out how much product is produced by a limiting region.
Okay, we are going to use your skills from what we just taught in this limiting and excess reagent problem. Here it is. If 5 grams of hydrogen reacts with 5 grams of oxygen to make water, what is the limiting reagent, or LR? And how much water is produced? So we start this as 2 simple gram to grams problems, one with the first reactant and one with the second. And if you did it right, you should get 44.68 grams of water for the first reactant, hydrogen, and 5.63 grams of water from the second reactant, oxygen. In this case, oxygen would be the limiting reagent simply because there is less of it, and hydrogen the excess. Now, to find out how much water is produced, you simply say the number of grams of limiting reagent there are, because that is all that is available. In this case, the answer is 5.63.
Almost finished. There is one more application of stoichiometry which is called percent yield. Percent yield is the actual amount of product yielded in an equation, which is generally given in the problem, divided by the theoretical yield of product in an equation, which is generally your answer to the problem, and multiplied by 100.
Take this problem for example. If 75 grams of carbon monoxide reacts with excess hydrogen to produce 68.4 grams of CH3OH, what is the percent yield? First, like we have learned, balance the equation. Next, do a grams to grams problem with what is given in the problem, 75 grams. Now take the actual yield, which is defined in the problem as 68.4, and the theoretical yield, which we found to be 85.7, and divide them. Multiply that number by 100 to get a percentage of 79.8%.
That's all for today on Chemistry with Ido, Jolie, and Lauren.
We hope you learned a little bit about stoichiometry today and its use in everyday life.
Wait.
Lauren, no.
Well, Jolie. Wait.
3.
Well, Jolie, stoichiometry is defined as...
You really-
Well, Jolie.
Wait,
stoichiometry...
start 1, 2, 1, 2.
No, wait. Wow, but wait.
Lauren, are you kidding?
Lauren, are you actually kidding? Go!
Measurement conversions. It's super simple and practical once you know the steps.
Wait, but there's more. Let's put some sprinkles into it.
keep going. One, two,
Turns out.
one,
Got
two, three.
Turns out chemistry and cookies have this pretty well measured. Did you know cookies and chemistry share a lot of things together?